Thank you. All right, so maybe from the title it is not completely clear, but this is a talk about general purpose programming languages interfacing with SQL databases. And you might wonder why finite maps and not relations. Well, let's start with the obligatory employees table, where you can find all the employees of a fictional company with their department and the salary depending on the value that they have for the company. And let's address the querying a database from a functional programmer's perspective. What might we want to do with this? Well, for starters, we may want to group the employees by their department. So let's suppose that we have a GAN operator that, given a relation, in this case the table employees, associates to every tuple in the relation a grouping key that in this case is just the attribute department from the original table. And what is the result of this operation, again, from a functional programmer's perspective? Well, here you have it already. It's a finite map, which is, in particular, the map that associates to each grouping key the subrelation of those tuples that match the grouping key. So for the grouping key department sales, you have the portion of the table of those employees that belong to the sales department. What do we do with a grouped relation with a finite map? For example, we might want to perform aggregation. Again, we suppose that we have a group-wise aggregation operator, this aggby, that takes the result of the previous query and produces, again, a new finite map where in the value part of the map, you will have an attribute average salary, which is obtained by taking the aggregate average of the salaries in that subrelation. And yeah, that's exactly the result you would imagine. Finally, we start with this grouped and aggregated relation, and then we think, well, that there is a French buyer, so we want to we want to convert this relation using French words for the departments, and luckily we have a dictionary table that translates sales to vente and research to recherche, and then we can write another query using something that is called comprehension, that everybody surely knows from set theory, but is very used in the functional programming area as well. So we can comprehend over the key set of the query Q2, that is the values over this column, and then over the values in each of the subtables associated to a certain key. So this Q2 star X means look up into Q2 the values associated with X and return the corresponding subrelation. And then you can comprehend also over the dictionary relation. And then you will produce a table in which the department is taken from the translation table and the average salary is taken from the grouped table. And the result will be exactly what you expect, that is the French translation, also converted finally to a standard relation rather than a finite map. Why am I showing you this? The area in which I'm working is called language integrated query, and essentially this is an expression to mean the support for safe database queries integrated within a language, within a general purpose language, not by means by libraries or worse by string manipulation of SQL comments, but as a sub-language of the general purpose language itself with all the safety characteristics that you would expect. The reason why we want it is that, for starters, it avoids the impedance mismatch, which is the difficulty of writing queries that are meant for a different language in a general purpose language. And also the fact that sometimes when we write queries by hand, they will fail at runtime even though they are statically incorrect. Also maybe because of a syntax error. This also avoids security vulnerabilities in case you were expressing your queries by string manipulation. You can optimize programs and queries together. And finally, this is basically the reason why we use general purpose languages to drive SQL databases, because in this way we can build complex dynamic queries automatically and safely in the case of language integrated query. Naturally, this appears to be a rather complex problem to match a general purpose programming language with a rather idiosyncratic declarative database language like SQL. A very successful way of managing this has been through the use of a core calculus called the nested relational calculus, which essentially identifies an overlapping portion of functional programming languages and SQL. What is it like? It's you can see it as an extension of the simply typed lambda calculus with collections. This sigma between square brackets indicates the collections of elements of type sigma. And these types can be obtained, values of these types can be obtained by using the operations in blue, which include the empty collection, the singleton collection, the union collection, and comprehension over a collection, as I've shown you in the previous slides. However, you may have immediately noticed that this sigma here is unconstrained, meaning that you can have collections of collections. So in a way, this calculus is immediately more expressive than SQL. But it's more expressive in a manageable way And this is what we want to do with NRC queries. If their type is a flat relation, we want to manipulate them through a rewrite system and finally obtain a normal form, which we believe that will be immediately translatable to SQL through select and union all. This is because there is a result called conservativity that says if you're using nested collections in your query, but the type of your query is flat, then it means that those intermediate nested collections aren't really needed. You can normalize them away and obtain a completely flat query. When instead the query has a nested collection type, then again we normalize it, but there is another technique called the shredding that allows you to slice the query in such a way that from a nested query you obtain a number of flat queries that can be run on the database. And there are two parts in blue here because originally these techniques were meant only with one collection kind, but they were extended to allow mixing sets and bags. And when you do that, you need to target a larger fragment of SQL. Right, so what is this talk about? This talk is about extending NRC with grouping and aggregation, as simple as it is. And we expect, again, to have flat-typed terms in the extended calculus normalizing to a form that can be immediately interpreted in SQL, and hopefully also nested type terms, nested type queries that can be normalized and then shredded and finally compiled to SQL. And what do we need in this calculus? Well, at a minimum, we want grouping, partitioning a collection into key indexed subcollections, that is finite maps. Lookup, that is from a finite map, retrieve the subcollection matching a certain key. And groupwise aggregation, which applies an aggregate operation to each subcollection of a grouped collection. And this is the syntax of the extended calculus. The main change is that the type of collections has been replaced by a type of finite maps, where the index contains the grouping keys, a row of grouping keys, each with their attribute name. And when this row is empty, basically we have the original case of pure collections, because that means that there is only one empty grouping key, and thus only one subcollection. How do the terms of the calculus change? For starters, now singletons need to come with their domain, which is the key associated to the singleton. This expression here means that this is a finite map that associates to the grouping keys n the singleton m, and nothing, the empty set, to everything else. Unions are still the same, comprehensions are still the same. Then we add grouping that I have already shown you. Lookup, again, that was also in the introduction, as was the aggregation. I want to spend one word more on this other comprehension here, because while this comprehension, the original comprehension, only works on pure collections and not on finite maps, this is the kind of comprehension that we use on finite maps, and it's a comprehension that works on the key set. So given a finite map n, take all the keys from the finite map n, and for each of these keys, take the grand union of the m. Naturally, the main point of having a calculus like this is to have a rewrite system so that once we normalize away our terms, we get something that can be translated to SQL. And it turns out that the operations that we introduced in this calculus allow a rather simple extension of NRC. For example, when we have a key value pair and we want to look up a certain key, well, in that case, we will just return the value provided that the key matches the one that we have provided in the lookup operation. Grouping operations also have nice properties. Grouping over an empty map gives you an empty map. Grouping over a union map gives you the union of the maps. And here I want to spend a second saying that in this case, well, this union clearly is not the union of collections, it's the union of maps, in a certain sense, of functions. So what does it mean? Does it mean the union of the graphs? No, not exactly. It means the point-wise union. Okay, so we are performing the union over the targets of the finite map, collapsing the collections that have the same key together. And we can also merge nested grouping by taking the disjoint union of the grouping keys. Okay. And the lookup operation has similar properties. The lookup over the empty map returns an empty collection, and the lookup over a union map returns the union of the lookup collections. The one case where we need a little bit of attention is when dealing with comprehension over a key set. That is this comprehension tagged here with the letter K. Clearly, comprehension where the generator is a singleton means that the only element we have to consider is that one key row in the singleton. So we just perform substitution over the head of the comprehension. And this operation, this comprehension operation, is also distributive over unions of maps. So the comprehension with a union generator is the union of the comprehensions. This seems so far so good, right? But it could have been worse, because this is actually not the form of comprehension that I originally considered, because what you would normally want to have is that from a map you retrieve key value pairs, right? Not just the keys. And in this case, we would substitute, when dealing with a singleton, we would substitute not just the key, but also the value. However, it turns out that that doesn't have good algebraic properties. In particular, if we used that form of comprehension as primitive, we couldn't have distributivity over union, because you remember that I told you union of maps is meant to be pointwise union. Well, this is incompatible with the distributivity law. Does this mean that when we are in this situation, we are stuck? No, it means that we will use the comprehension just over the key set, and then the auxiliary lookup operation to deal with the values, and everything works fine. What do we have now? Now we only need to analyze normal forms and wish that the normal forms are simple enough to be converted to SQL. And you see, on the left column, you have the normal forms of flat queries in the original version of the calculus, and on the right, you have the normal forms on the extended calculus. And what are the changes? Well, the changes are that where there were singletons, you need to also consider the grouping keys. You need to consider two forms of comprehension generators, one for values, one for keys. You need to consider the operators that we have introduced, grouping, lookup, and aggregation, group-wise aggregation. But it's not so bad. It's still pretty rational, and it can guide an implementation. And the implementation works like this. So you remember, as I said at the beginning, NRC is more expressive than SQL because it has more expressive types. And for example, in this extended calculus, finite maps are a type that doesn't exist in SQL, but that is very benign because there is an isomorphism between finite maps and collections of key value pairs. So essentially, what we need to do to translate to SQL is to tag attributes in relations as keys or values. This is the case where we want to translate, this is the main case actually, where we want to translate a comprehension with a head that is a singleton with a key value pair. And that means that we can simply translate it to a select from statement as long as we tag the row 1 attributes, which are keys, as keys, and the row 2 attributes as values. For aggregation, we do something similar. This is where the group by statements come from. So if we are aggregating a finite map Q, we will need to group by the keys of the query Q while using Q as the input for the select, and return as the output the keys of Q and the aggregation. And this 2 over here, which was not in the original query, is the way we tag things as values. So to sum up, this was our initial goal, and what I have shown you is when you have flat typed NRC lambda gamma queries, you can normalize them and obtain normal forms that can be translated to SQL. But the paper also shows that when you're in the nested case, you actually can extend the shredding algorithm to work with finite maps as well, which is great. It was unexpected and a low-hanging fruit. There is another thing that I haven't mentioned. In this talk, I have discussed this calculus as if it had only one kind of collection, but actually in the paper, mixing set and bags is allowed, and there are some extra difficulties, but they are the same difficulties that you used to have in the version of the calculus with sets and bags, but without finite maps and aggregations. As I said, we translate to idiomatic SQL grouping queries, meaning that grouping is translated to grouping. It could have been translated with something else like correlated subqueries, but that would have had horrible performance. I haven't told you that the rewrite system is strongly normalizing, which is another nice property, because it means that you can choose the evaluation strategy that appears to be more efficient, and you know that you will always reach a normal form. And as I said, the full paper also extends to multiple collection kinds and to nested relational queries. Yes, to conclude, as far as I know, there have been other attempts at core calculi for grouping and aggregation, but this is, as far as I know, the only case in which you have several desirable properties: higher order functions, finite maps as first-class values, and the possibility to deal with nested finite maps, and a full proof of strong normalization. And this is actually implemented what you have seen in the talk is implemented in links. I wanted to say in the released version of links, but actually it wasn't released in time for PPDP, so you would need to get it from the GitHub repository. I mean, this is a good thing. In a commercial implementation, there are commercial implementations of language integrated query with grouping and aggregation, very used and very successful. But every now and then, a bug comes out because there is an imperfect understanding of the theory, and this is a step forward in a better understanding of the theory. And yes. In the paper, there are more details, and as for the implementation, what is not implemented yet is the shredding part, that is the part that deals with the nested relational queries, but the theory is sketched out in the paper, and it is rather simple. And this concludes the talk. Thank you very much.
So the obvious encoding is you could use is with just key value pairs, as you've shown repeatedly in here. So the benefits of this approach over simply doing that is that it's more efficient to compile into SQL grouping.
The benefit is that you don't lose the you don't lose in the compiled version the separation between keys and values, because once you use the isomorphism, it just becomes a collection. It's not a finite map anymore, and you can use that as part of an optimization process. And yes, if you have grouping performed in terms of group by operations rather than correlated subqueries, as you would end up doing if you just converted everything to key value pairs, that's usually considerably more efficient. And I can tell you that I had a development version that performed that didn't use group by and performed everything just in terms of key value pairs, and it was horribly inefficient.
Thank you.
Other questions?
I have a slightly more abstract question. In your core calculus, you have function types. What about an extension of this calculus where instead of function types you have essentially primitive relations? So an application of a relation would not necessarily normalize to a value, although it would normalize to a relation. Would that still be work, or is it possible to make it work with that?
I mean, in a certain sense, that's what finite maps do. Okay, the output of these finite maps is always a collection. So that multi-valued part of that is already included. Clearly, functions and finite maps in this calculus are rather different because finite maps are a glorified table by virtue of being finite, whereas functions don't have to be finite. So it's.
So this was also a question which I had at the beginning. You also showed in the first version you had also collections over any type, and therefore I was also puzzled if you had functions and you want
yes.
a set of functions. You need equality on functions in order to have sets. So how does it
we
work?
do well in the calculus. You have them, but when you want to translate to SQL, you will limit yourself to types that can be translated to SQL. So a collection of functions is not something that you are going to translate to SQL. But you use functions as intermediate steps in building queries. They are just normalized away by the right system before you send everything to SQL. And there is a complication with that when you deal with the case where you mix sets and bags, in part because deduplicating functions, like having a set of functions, as you were saying, you would need to have an equality between functions, and that is unspecified in the calculus how you would do it, right? So, I didn't tell you, but I hinted here. Here you see this TNC. That this was to say that yes, comprehensions have good rewrite rules, but there are a few cases when they don't. That is something that appears not really in this work, but in the previous work that mixes sets and bags. And again, the reason is related to the fact that you're not always able to normalize away functions in a collection when you mix sets and bags. So in order for that to work, you want not to have functions within sets. You can have them within bags, but not within sets.
Yeah, so thank you very much again, and all the speakers also.
Thank you.